Hey everybody, how's it going? We've been in chapter 12 and we've been talking about statistics a lot so far, and now what we're going to do is move on into the world of probability. But first we're going to talk about outcomes. So today we're looking at outcomes and theoretical probability. First, outcomes. When we talk about outcomes in math, what we're really talking about is the number of possible ways that a scenario can turn out. So if you're rolling a die, there are 6 possible outcomes. You could roll a 1 or a 2 or a 3 or a 4 or a 5 or a 6. When you're flipping a coin, there are 2 possible outcomes, heads or tails. You can see here that outcomes, we're just talking about the number of ways that a scenario or an event can turn out. So if you're pulling one card from a deck of cards, there are 52 possible outcomes. Now, if we wanted to make a list of those 52 possible outcomes, what we would be doing is creating what's called the sample space. The sample space is the list of all of those possible outcomes. So for drawing a card out of a standard deck of cards, the sample space would look like this. You have 52 possible cards, and you could draw the 6 of clubs, or the 2 of diamonds, or the king of spades, etc., etc., etc. The list of all those 52 outcomes is called sample space. So what's the sample space for flipping a coin? Heads, tails. Pretty simple. What's the sample space for rolling a die? 1, 2, 3, 4, or 5, or a 6. All right, now let's make this real. Let's apply this to something in real life. All right, this morning I had to think about outcomes and sample space because I was getting dressed and I looked in my closet and I had 6 sweater vests to choose from and I had 4 clean shirts to choose from, and I had to figure out how many outfits could I make with these 4 shirts and these 6 sweater vests. In other words, how large would my sample space be if I tried to list out all of the possible outcomes here? Because I could have like the yellow sweater vest with the light gray shirt, or I could have the gray sweater vest with the blue shirt, or I could have the black sweater vest. You get the idea here. But I didn't want to make a list of all those different outcomes because that might take me a while. So I thought, I think I know how to solve this problem. I have 6 sweater vests and I have 4 clean shirts to choose from. What if I just multiply those 2 numbers together? That gives me 24, and actually 24 is the number of possible outfits here. My sample space would be 24 outfits large. And if you want to, you can pause this video right now, and you could make a list of all of those combinations of different sweater vests with different shirts. And if you did all of them, it would be exactly 24 outfits large. So a shortcut to finding the size of the sample space is to just use multiplication. Now, in reality, I can't just wear a sweater vest and a shirt. I got to put some pants on too. So this morning I had 2 clean pairs of jeans to work with, and if I had 2 clean pairs of jeans with my 6 sweater vests and my 4 shirts, and I multiply all that together, I just doubled the amount of my outcomes. I just doubled my sample size, and I've got 48 possible outfits that I could wear this morning. All right, what I'm showing you right here is something called the counting principle. It's also sometimes called the basic counting principle or the fundamental counting principle. And what it says is just multiply all these numbers together. So if you're trying to find the number of outcomes and there's multiple events within the whole overall event, just take the number of possibilities and multiply them all together, and you will find the size of your sample space. You will find the number of outcomes just by using the power of multiplication. Interesting. All right, so now I'm really going to test you because I had to put some stuff on my feet too. So I had 3 pairs of Chucks, 2 pairs of jeans, 4 shirts, and 6 sweater vests to choose from. And if I do 6 times 4 times 2 times 3, I had 144 possible outfits that I could have put on my body this morning. So I'd like to think that what I'm wearing today is a very unique combination of clothing, because it is. All right. How many different possible phone numbers are there? Have you ever wondered that? Well, if we're looking at the number of outcomes when we're building a phone number, we have to kind of look at the standard way that we build phone numbers here in the United States, where we have a 3-digit area code and then 3 more digits and then a dash and then 4 more digits after that. And we have to look at the very first digit. Okay? When we pick the first digit of a phone number, there's 10 different numbers that could go in there. It could be a 9, 8, 7, 6, 5, 4, 3, 2, or a 1, or a 0. And then I have to multiply that by 10 because the second digit could be 10 different numbers as well. And then I have to multiply it by 10 again. and this could be 10 different numbers, and that could be 10 different numbers, and this and that and this and that, and the last one could be 10 different numbers. So if I want to know the total number of possible phone numbers there are, it would be all those 10s multiplied together, which is 10 to the 10th power. And the answer to this problem then comes out to 10 billion phone numbers that are possible in the United States. And we did that just using the power of the counting principle, which tells us to multiply those numbers together. All right, now I want you to try. Here's a practice problem. It'll be a little bit easier. Instead of 10 digits, how many different 5-digit zip codes are there possible? You can pause the video, try a little work, and see what you come up with. All right, now let's talk about Monopoly. I like to play Monopoly because I like games and stuff. The other day I was playing Monopoly and I was on Tennessee Avenue and I really wanted to get to the free parking space. It was 2 spaces ahead. I was rumbling those dice up in my hand, and right before I released those dice onto the table, I prayed to the gods of Monopoly, please, Snake Eyes, give me Snake Eyes, give me a 2 so that I can get that cash. How likely is it that I would have gotten Snake Eyes? Well, here's your sample space. When you roll 2 dice, you can get a 1 and a 1, or a 1 and a 2, or a 3 and a 3, or a 4 and a 6, or you can see all the different possibilities there. So out of all those possibilities, there's only one that gives me Snake Eyes, that gives me 2, a total of 2. So I only had a 1 in 36 chance of getting a 1 and a 1. Now, I didn't really have to list the whole sample space here though, because I could use the counting principle instead. When I rolled the first die, I had a 1 in 6 chance of getting a 1, right? When I rolled the second die, I also had a 1 in 6 chance of rolling a 1. And using the counting principle, I can just multiply those 2 fractions together to find my overall probability, because I do 1 times 1 on the top, 6 times 6 on the bottom, and I have 1 in 36 probability of getting Snake Eyes. What I'm trying to show you here is that the counting principle works for probability fractions just like it helps us to determine the total number of outcomes. So let's try another one. What's the theoretical probability of flipping heads 3 times in a row if you're flipping a coin? When we talk about theoretical probability, what we're just asking is, in theory, how often should this happen? Is it likely, unlikely? I don't know. Let's find out. When you flip the first coin, what's the probability of getting heads? You have a 1 in 2 chance, right? And then you have a 1 in 2 chance on the second coin, and a 1 in 2 chance on the third coin. And if you multiply that all out, you get 1 times 1 times 1 on the top, 2 times 2 times 2 on the bottom. So in theory, you have a 1 in 8 chance of getting heads, heads, heads. And we did this by just multiplying our probability fractions each time. So what we're basically saying in this video is use multiplication to your advantage, because it can help you with outcomes and it can help you with probability. Finally, it's your turn. I have a challenge. If I picked out an outfit completely at random, blindfolded, grabbing clothes out of my closet, what are the chances that my sweater vest would have blue on it, my shirt would be gray, and my jeans would be faded? You tell me, and I will see you in class tomorrow.